Okay, so this is a little bit of a harder thing to figure out how to do a tutorial with because ultimately, performing an analysis is something that is kind of fundamental to anyone doing this work, whatever experiment you're in, it doesn't really matter. So most of what I'm going to talk about today is trying to walk you through the kinds of things you'll need to consider um, to really make sure that you're kind of starting an analysis in the right way and that you're integrating yourself with the working group that you're a part of to make sure that the conveners are able to kind of vet the work that you're doing before we start releasing results. This is how it works in every collaboration that I've known or been a part of, and Epic will function very similarly. So basically, I'll show you what we're gonna, talk through. I have code that generates all the plots and everything that I show in the slides. I'll make it available after the fact on GitHub if you just want to see how these things were generated. But ultimately, the reason that we care about doing this sort of thing, so we've had all these tutorials in the past of how to do things in the Epic EIC working environment. So EIC shell, running simulations, EIC recon, extracting information from EIC Recon, all of that has been presented and is existing online already. But ultimately, for us to be able to put things together into our documents that we need to get our baseline and construction moving for the EIC, we need to have results which both show the true performance of our detector and allow us to really make sure that we've chosen the right technologies and that we can kind of baseline all of it. And then we need something that we can actually present to theorists that they're able to use to figure out the capability to actually advance the field on the scientific side. So for example, if we show a result that doesn't have corrections for the detector effects and doesn't have knowledge about what luminosity was assumed, it's very hard for a theorist to then take that information and figure out how it would be a part of a global fit, for example, and see how much it might improve our understanding of some aspect of a PDF. So ultimately, part of the discussion today is also how we can actually handle things in a way that's realistic. It's very easy right now for somebody to pull something out of EIC Recon and make plots and look, I did an analysis. That's not an analysis. That's running some for loops and extracting some histograms. There's a lot more to it to go from that level to something which is then at the standard for a normal physics analysis. Ultimately, the physics working groups are going to be the ones that enforce this, but part of the goal here is to develop a set of tools that make it easier for analyzers to be able to present something that can allow their analysis to move forward so the working group conveners can be on the same page. So for any of these analyses, we have to really have an understanding of the detector effects and be able to correct for them. This goes from a simple side to acceptance corrections, which we will talk about in this talk, all the way up to something a lot more complicated like unfolding. We will not talk about unfolding in this talk because that in and of itself is probably an entire topic for a workshop, and I don't want to spend an hour arguing about that. That already happened in Frascati. But ultimately, it's that kind of range of things that have to be considered when you're trying to correct for things and make an analysis go from, laden with detector effects to one which is more invariant on the physics side. And then, of course, one of the things that's very important, especially for folks who come out of, say, heavy ion, which is where I came from, measuring things on the DIS side is generally both easier and more difficult. It's easier because the final states tend to be simpler, there's less particles, but it's often more complicated because you don't take as many ratio measurements. And ratio measurements, many of these annoyances can cancel out, which makes life easier. Anything you're measuring that's a cross section means you have a lot more work to do to make sure that you apply all the correct corrections, that you apply the luminosity factor correctly. Each of those things has an associated uncertainty, and it's very, very important to get those things right. And so as we kind of move toward the DIS physics world, for those of us who are not from that field, we have to start taking these things into a lot more careful consideration than maybe we did in the past. And the most important point here is that at the end of the day, if we measure something in Epic and something similar is measured in the same range of kinematics from a different detector, they better be consistent. If they're not, then we have to assume that what's happened in the three-body problem is coming true and that the SOFONs are here to distract us from being able to understand physics. Sorry if you don't get that reference. So for today, you don't really need to have your laptop ready to run code. I thought about this a lot, and I think it's not really useful for this particular discussion. It's really better to present the information and allow you to ask questions. Um, I kind of assume that you already have familiarity with how to extract things from EIC Recon, although I will review a couple of very minor points with that. I use T-Tree Reader for things, but you can also use data frames. It's really up to what your particular, understanding and comfort is. So the example that I'll show is based on T-Tree Reader. I'll also assume that you have some basic familiarity with Epic as a detector, but I will just very quickly run through it on the next slide. And as I said, at the end of all this, I will provide some of the code that I've used to generate these plots on my personal GitHub, but I'll wait to post it until I get some feedback before I have to, then make changes, just so you have it available if you want to run some of this stuff yourself. So I think most of you are familiar with Epic, but just to make sure, this is what the main detector looks like. This is kind of what a generic DIS event might look like. And so you have your scattered electron, which is important for every single possible analysis. You'll have some hadronic final state that'll go mostly in the mid or forward rapidity region. And we have, of course, combinations of tracking, calorimetry, and PID. Basically, we kind of break the detector up into five distinct regions. So the main detector is backward, central, and forward. And then, of course, as we zoom out from the main detector, we also have the far backward and far forward regions, which are important for doing all the exclusive physics and also for taking luminosity measurements. So the luminosity measurement is important for any kind of spectra you want to measure in Epic. Now, my expertise is on the far forward side, and so the example I'll show today is from that region because I'm too lazy to do something different. And so ultimately, just to introduce where the particles will end up going that we'll mostly focus on, we'll mostly look at a scattered proton going into the far forward region. This is kind of a zoomed in thing, section of the actual detectors in DD4 HEP. And the main detectors that we'll care about today are the Raman pots and B0. And what's really important here is that these detectors are really for capturing scattered protons that are, for all intents and purposes, effectively collinear with the beam. And so you can see the pseudo rapidity coverage for these detectors is very much in the forward direction. This is outside the main detector, but it doesn't mean the main detector is not important. We'll come back to that a little bit later. I just picked one example to make things easy today. So the ones we'll really focus on, as I said, are the Raman pots, that pseudo rapidity greater than 6, and the B0 detector, which is a little less aggressive in pseudo rapidity. For accessing the information in EIC Recon, as was shown in previous tutorials, the main thing here is that you have this branch structure inside of the output files from EIC Recon. And there are many, many branches in those output files. Some of them are specific to individual detectors, some of them are more holistic. In general, one of the main areas you would need to focus on would be something like reconstructed charged particles. This, of course, is for charged particles, but will not include photons and neutrons. There's reconstructed particles without the charged for kind of a sum of everything. And then the idea here is that in this very simple kind of code block, I normally put things on a long file list so I can read all the root files one by one. And the way you can read files in one option is to use the T-Tree reader. And so you basically pick the branches that you care about and look at the leaves within that branch that you want to access, and you have an array or a data structure that you can use to store that information in real time and then loop over all of it. Data frames basically removes the need to do an event loop. I don't like that. I like having an event loop because it makes me feel safe. But ultimately, our data frames are actually a little bit more efficient. And so if you're used to using those already, you should probably use those. But I like the T-Tree reader. So really and truly, if you're ever starting an analysis for the very first time, one of the first things that you should do is open up one of these files. Just grab one, single files, maybe 20 or 30 megabytes, and open it up and look at what is in there and figure out, okay, what things are relevant for the thing that I'm going to be measuring. So if you're not measuring something in the far forward region, you probably don't care about the Raman pots. But you're almost always going to be looking at some charged particles because you need to get a scattered electron, for example, and you'll need to also look at maybe whatever else is in the main detector. And so these kinds of branches are of general interest to pretty much everybody. And so, this kind of familiarity is important. You should definitely make sure you have a good understanding of what's here. And if there's something that you're not sure about, message the help desk and ask. I mean, this is the whole reason we have the Mattermost set up is so you can ask questions about, detailed aspects of what's existing in the various elements of the framework. So for any analysis, one of the first things you really need to make sure you do is identify the correct data set. This may seem like a stupid thing to say, But there's been many times when someone has asked me a question and they're not even looking at the correct data set. It can be a little challenging. There's a lot of information that's output from the simulation campaigns, including whether or not you're looking at the correct simulation campaign. We do one every single month, and it's very often a lot of things can change in the framework. Everything is still very much in flux because we're still working on trying to get things to a more stable state. We don't even have, final design concepts in place for everything for the detectors yet. So it's very natural that things are going to be changing on a regular basis. And so you should make sure that you're really careful to know what version of the simulation campaign you're looking at, what the date stamp is, and then whenever you're presenting results, that you've made it clear in your presentation what you are actually pulling from in terms of the simulation campaign. Another thing you should always ask is whether or not this is a pure single process. And I'll come back to this at the end, but nothing that we're looking at right now includes background, but it will soon, but not for everything all at once, because every single set of events has to be merged with some background. And by background, I mean primarily machine background, because you'll have events where a particle beam will smash into a latent gas that's floating around in the detector, and that'll be essentially a fixed target collision, and that will pollute the actual things we want to measure. But another thing that can be considered for background is other physics processes that can distract you from being able to find the thing you want to actually find. In real life, this is most of what we have to deal with, but in simulation, we barely have to deal with it. And we're trying to, include that realism as we go forward. So for right now, you're pretty much only going to be seeing the second bullet point, but you should be noting in the back of your mind, hey, this seems really easy. It's not going to be forever. At some point, we will have the backgrounds included and you will have to start adjusting for it. So be thinking now for your analysis, what kinds of backgrounds could make my life difficult and how should I start considering how to handle them now? The other thing that's really important and that you should do right away, that's why I tell you to open up the EIC recon file early, is it's very annoying to have to go back and forth to figure out what branches you need in your code and you'll waste a lot of time on it. So you should basically go through and figure out what branches you need before you start doing any event loops. Write all those branches down, get them included into your code so all the information you need is there. Um, it's also the case that in some instances over the last few months that the information in a branch has changed. A perfect example is last summer when we started adding the PID. So right now, the PID detectors are primarily not using realistic full reconstruction to identify particles. Instead, we're using a parameterization in the form of a lookup table. So if a particle is hitting one of the PID detectors in a certain range of phase space with a certain momentum, then the lookup table will basically tell you what the probability is that that particle is of particular identity, pion, kaon, proton, whatever. And then the highest probability for that is stored as that particle's identity in the EIC recon output. So we, as a community, made those changes, but not everybody really fully understood what changed. And so it created some confusion. So for example, if you have a particle going into a detector where there is no PID, those particles were automatically assigned a value of 0. And most people didn't know that. They were using the actual PDG values. So these things can change fairly often. And so that's okay. If you run your simulation reconstruction and analysis from February to March and you see a big change, that's not necessarily meaning your code is broken. It could just mean something changed, and you should go and look at the change log on GitHub to see what new things happened in the release, or ask somebody in your working group or on the help desk. And then when you actually go through and do the loop over particles, you should, really start thinking about QA histograms. In the exclusive working group, we've already started putting together a list of required histograms that everybody must produce. And these are simple things: Q square, 3 momentum, PT, eta phi. And I'll show you why that's important in just a moment, that we really have this for kind of every single analysis, because it can be one of the easiest ways to immediately see if there's a problem. And then from there, it's really going through and doing reconstruction and performing all your corrections and doing systematics. Now, for anyone who's done any of the simulation part of things, you'll probably have heard of this concept of the afterburner. So the afterburner's job is to take a Monte Carlo sample and apply all of the necessary beam effects that are, more or less realistic, as well as apply the crossing angle. So the collisions in EIC don't happen head on, they happen at a 25 milliradian crossing angle for epic. The second detector will have a slightly different crossing angle. And that has consequences for the information that comes out when you actually look in EIC recon, even at the level of the MC particles, not just from the reconstruction. There is no automatic handling of this for the reconstructed particles. There is some automatic handling in this for MC particles, although it's kind of imperfect. It's something we still need to fix. But the really important thing here is that this frame here that's boxed on the right side, that is the actual collision frame that we will see in real life. It's modified a little bit because it makes it look like the electron has no angle. In real life, it does have a small angle, but the sum of it looks like this. And so our frame inside of the EPIC simulation framework is that the electron is collinear with the minus z direction, and then the proton has the full crossing angle. And so the important thing here is that whenever you do any kind of analysis, you have to make sure you account for the crossing angle. It really just amounts to a couple of Lorentz boosts, and most of the stuff Root can do for you. You don't have to do anything really by hand. But it is important that you are consistent. So if you compare, especially MC and reconstruction, if they're in different frames, you will, of course, not get the same result. And that's artificial. So you might see, oh, our reconstruction really sucks for some reason. First thing you should make sure you did is actually account for the afterburner. For things at mid rapidity, it can become less of an issue. This doesn't affect things at pseudo rapidity right in the middle of the detector. But the minute you start going a little bit forward or a little bit backward, it will start to have an impact. And so you need to make sure you handle it properly. And as I said, there's no automatic handling this for the reconstructed particles at the moment because we haven't exactly figured out what branches we would apply this to because it can very quickly generate confusion. There is a little bit of a special case with the Roman pots. It's a little bit more detail than we need for this talk, but if you're curious about it, you can ask me later. Okay, so let's assume that we've got our EIC recon output. We've already extracted all the branches that we need. You learned that in the last tutorial. So let's start looking at what these kind of initial QA plots might look like. And so the questions we want to ask ourselves when we do this are the particles going where we expect them, right? If we see a proton that we expect to go in the forward direction sitting in the backwards calorimeter, that could be an indication that maybe we did something weird or simulation might have been weird. Our generic efficiencies what we expect them to be. If we know a particle should be in a certain part of the detector and we never see it, that could be a problem. And then, ultimately, before you really start doing any physics analysis, and that means trying to do anything where you're reconstructing something you can actually use to learn something about the underlying physics, you really have to make sure that these QA plots are fully sensible and that the working group views them as fully sensible. And so in the exclusive working group, we've already put together, Kong and Raphael put together a list of all of the plots that one would need to generate before they can even consider starting to analyze the physics, right? And this list of plots is kind of a starting point that everybody has to be abiding by so we can make sure that we're all on the same page and that there's no obvious problems. And I should also note here that where the particles go in the detector is not the same thing as whether or not the detector did a bad job of reconstructing their kinematics. These are two different issues, and we will discuss those two different issues. I see something in the chat. Let me see. We don't use GenFit. No, we use ACTS, and ACTS includes some Kalman filtering, but ACTS is its own tracking package. GenFit is another tracking package that's used in quite a few experiments. We use it in STAR, but we're using ACTS for our tracking. Okay, so this is just a quick example, and this is the physics example that I'll use throughout the rest of the slides. So this is a deeply virtual vector meson production, exclusive vector meson production for JSI. This is using the 10 on 130 beam energy. And so the first thing we can look at is the scattered proton kinematics. So I'll focus on the scattered proton just because I can't focus on everything, and that'll just make life easier. And so you'll see here, I'm just showing the acceptance for right now. And so in this case, the scattered proton is going to go into two different detectors in the far forward region. So these protons are not in the main detector. They're going down the beam line toward these far forward detectors. In red, you'll see the particles going into the Roman pots, and in green, you have the particles which go into the B0. And what's important here is I plotted both transverse momentum and theta, and that's on purpose. So theta is basically the actual angle, scattering angle that it has. And in theta, there should be no overlap between these two acceptances. because there's a beam pipe between them. So the particles going down toward the Roman pots are going down through a beam pipe. And to get out toward the B0, they have to basically not be in that beam pipe, and that thickness of your beam pipe gives you a natural gap in your acceptance. And so right here is a perfect example of a QA plot that would tell someone like me, who is a detector expert, if your analysis already has a problem. And that's why these kinds of plots can be so important. But for PT, it's a little bit different because PT is the momentum relative to also the longitudinal momentum, and you can have longitudinal momentum that is much different from what you started with. You can actually have a lot of loss, and that's what you see here in the PZ distribution. And so you can see in PZ, this is the peak values at roughly the beam energy, but we can actually have values that go down to much less than half the beam momentum, and that's why you can have this overlap in PT. But angle is something that is basically fixed on the geometry of the particle scattering. And so, that's why you want both of these things, because ultimately one of them will tell you a lot very quickly as to whether or not you've done something wrong in your detector. And this is really important for us as we go through any analysis, because we can quickly see if something is wrong before you've wasted time trying to do a full analysis. It'll save everybody time and headache, and we won't have as much stress trying to figure out if something is really fundamentally wrong or if it's something very simple. You can also go a step further and look at, two-dimensional distributions. These can be helpful to understand if you have some, specific issue that's causing you to lose particles. So this is azimuthal angle versus polar angle. And so you see the gap again. This is between the two detectors. So you naturally have no acceptance there. And then you can see there's a small region in the B0 where you effectively have 100% acceptance. And then in the Roman pots case, you don't really have 100% acceptance. And in large part, this is because you don't always have the full beam momentum. If you have some momentum loss, some of those protons can get steered out of the beam line and not make it to the Roman pots. And so this is the kind of stuff that is very simplistic. It's very easy to help for debugging for the detectors, and it also helps you as an analyzer to understand where these particles tend to go, what detectors they tend to land in, and why we might lose them. This is really important because ultimately, if you're losing particles you don't expect to lose, it could mean there's something even wrong with the geometry description. And so this is one of those things where the feedback that you as an analyzer give is not just about whether or not you might be doing something wrong. It could be that something has changed in the simulation framework that is incorrect. And that does happen. We make a change, we don't realize that it actually has a knock-on effect. And an analyzer showing us these simplistic plots can easily make us go, hey, something's wrong. And we've already seen that happen in the exclusive working group, and it's very, very important for us trying to debug all the detector aspects of the simulations. So we'll come back to this acceptance aspect and efficiency aspect a little bit later. One little tip of how you can do these kinds of plots is to basically say, if you find the particle in the reconstructed branch and you're sure it's the right particle, when you plot the information, simply don't put the reconstructed vector into the histogram. Instead, use the Monte Carlo vector. And that will allow you to get these acceptance plots where you don't have the smearing from the detector reconstruction. You're using the Monte Carlo particle information, assuming that you found the particle in the reconstructed branch. That's really all we mean by acceptance only distributions. So it's basically the reconstructed without using the reconstructed vector. Okay, so before we kind of move on to the next chunk here, does anybody have any questions? Because I realize I just dumped 20 slides of information fairly quickly, and I take for granted, whether or not people are comfortable with this stuff. So before we move on, any questions? Okay. So one of the discussions that we've had, and we don't really have a final answer to all of it yet, is whether or not we standardize everything or have the analysts do all of the reconstruction of components. So the major kinematic quantities, in some cases, are already in the output from EIC Recon. So aside from branches that are related to detectors, aside from branches that are related to final momentum vectors, we also have branches that are related to the reconstruction of specific quantities. So in one of these cases is the inclusive quantities, the inclusive kinematics. So we have things like Q square already reconstructed in EIC Recon in kind of a standard way, as well as a couple of alternative ways. And the idea there was that something so fundamental to every single analysis perhaps should be standardized to avoid errors. But But there is a little bit of a drawback to this potentially, and that's that it takes the responsibility off of the analyzer and potentially means the analyzer is learning a little bit less about the things they need to learn for their education. And so there is kind of a give and take here, because ultimately the job of the collaboration is to produce, sound scientific analysis that can be used to advance the science. That's the goal. But the secondary goal ultimately is that we produce also scientists who are independent and able to, do the work going forward. And so there's a little bit of a give and take that has to be considered here. And so one of the things that I would highly recommend, because this discussion is not one which is finalized on every single point, as an exercise for you, in any place where you have a quantity that is pre-reconstructed in EIC Recon, I highly recommend that you calculate it yourself and make sure you can get the same result. It's good for your education, but it's also good, once again, for error checking, because as we build all these branches in EIC Recon, some of them have been very well vetted, but we'll be adding more, and it's very possible that a mistake can happen. And so if the analyzers aren't doing these things on their own at some point to check, then we potentially have a bug that persists for a very long time. So this kind of thing is very important. It's not a discussion which is finalized yet. You'll probably hear a lot about it in the working groups. Um, and there's, a lot of trade-offs that come here. For example, if you have more control over particular variables, it allows you to control for some of these in your reconstruction and have this trade-off between things like purity and efficiency. And I'll talk about that in just a moment. And that's really important when you're evaluating systematics. The PID is a perfect example of this, and that's the example that we're going to use. So as I said before, right now what we have for PID is these lookup tables. And so basically the lookup table will automatically figure out what particle it most likely is, and that'll get stored in EIC Recon, and the user has no control over how probabilistically sound it was that that particle was the right one. In most analyses that I've seen, using PID detectors to date, there's access to this information on the user end. And so a good example is PID in STAR. So we have a time projection chamber in STAR. We also have a time of flight system, and I'll get there in a second. And a time projection chamber is a big tracking volume, and the idea is that as particles go through, specifically at fairly low momentum, the amount of energy they lose as they ionize the gas can look very different particle to particle at low momentum. And so we have an understanding of the physics of how this actually happens, and so we use the Bischel function to parameterize the expected DEDX curve as a function of PT for each particle species. And then we can measure the DEDX from the ionization profile that we get in the gas. We can actually see this based on how much charge is deposited point by point as the particle goes through. And then from this, you can come up with an n sigma value that can be used to determine how likely it is that that particle is a certain species. And so we normally use something like 3 sigma to decide that something is most likely a certain kind of particle. But there are some regions where you have huge overlap, and basically once you get to, a little over 1 or 1.5 GeV in transverse momentum, this approach to PID already becomes very unhelpful. And so, you start to get values of 3 sigma for multiple different particle hypotheses, which is not helpful. But the whole point here is that as an analyzer, you have in principle some control over this, and this is true for many of the things you might try to measure. And so you can basically control how aggressive you want to be in assuming a particle is a certain species. So you can say do a 1 sigma cut instead of a 3 sigma one if you really, really want to have a high amount of certainty. And then you trade off between purity and efficiency. So the idea here is that, um, we already talked about the probability here, but the idea here is that basically if you are more sure the particle is what it is, you're excluding other ones that potentially could also be that particle. So if you say have a proton and you want to be sure you found a proton and you have a really aggressively stringent n sigma cut, you are by definition throwing away some number of good protons because you want to be so sure. So you might have a very high purity, but now the efficiency is very low and that can harm your statistics. And you can measure all of these quantities statistically and assign a systematic that comes from how tight or loose that cut may or may not be. Now, you can also make use of other detector. No, this is the definition of purity and efficiency here for those who are unfamiliar. So ultimately, the main takeaway here is there's some point where the information overlaps so badly where this trade-off doesn't even make sense anymore, right? And so In this case, then you have to look to other detector information. And so in STAR, at least, we've employed, two different kinds of PID. So we also have a time of flight system. And so you have the DEDX and the TPC on one side, and you have the time of flight on the other. This is measuring the velocity of the particle. And so as the particle gets very relativistic, the bands, of course, start to coincide once again. And so you start to lose discriminating power at very high momentum. But in principle, you can use both of these pieces of information together and allow yourself to be even more sure that you are able to get a balance between purity and efficiency. And this is kind of a picture of what it could look like to use both pieces of information together. So now you have the DEDX information on one axis from the TPC, and then the inverse beta information from the velocity that you get from time of flight. And you can see these nice ellipses that very clearly separate different particle species, and you can cut on those ellipses to get very pure samples with still very high efficiency. In EPIC, our PID is much better than this. In EPIC, we have Cherenkov detectors, so we can have PID up to very, very high values of momentum. But the same kind of give and take will have to happen because ultimately, we will not just have a single particle going through the detector. And that's really one of the most important points here that is right now very much glossed over. We will have backgrounds, we will have other physics processes that pollute the thing we want to try and measure. And so our detectors have to be stress tested against much more harsh working environments than we've currently stress tested them. And so, what we see here for STAR, this is in an environment with heavy ion collisions with thousands of tracks. And this is the kind of thing we could achieve even in those environments, but it's not easy. And so we have to do the same kinds of studies in EPIC as we start to integrate background into our simulation samples. And so that's why I say be thinking about when you're trying to do simulations right now without that, how those backgrounds might make your life more difficult and what kinds of things you're going to need to consider. It's better to start thinking about those things early. Okay, so back to our original example from earlier. So we want to measure something from, actually, before we do that, any questions about this? Okay. So we want to actually start moving on to measuring something in EPIC. So earlier I showed the distribution of the scattered protons that we get from this JSI production case. So the scattered proton is a very, high pseudo rapidity. It's in a very narrow range of detection for the FAR4 detectors. And we want to use that information now to try and extract a quantity that is actually physically relevant. And so we can use the output from EIC Recon to reconstruct particle information from the Roman pots and the B0 together. This basically represents our full capability to measure the protons in that region of phase space. And the black is what you get from MC particle. And there's a huge obvious issue here, and that's that you have this massive gash in the middle. And that's coming from the fact that you do not have full detector coverage in that region. There is a physical gap there, and ultimately, you cannot measure for a certain part of this because there's no way to put a detector there. And so if you were to take this distribution as is, you wouldn't really be able to do anything with it to actually extract physics because you can't really get a full sense of the normalization of the black distribution from the different colors here. You see that there's only one region where you have enough acceptance to really get back up to the same, normalization value. And obviously, here you have no way to evaluate how much bin migration you have. And you have some region here even where you have a not fully symmetric acceptance. And so you have loss even in an area where you in principle have coverage. And so ultimately, if you wanted to try and do the physics here, which is to measure the cross section as a function of t, correct it fully, do a Fourier transform to get the spatial distribution of the gluons, for example, the red and green points here that come as the reconstructed information directly from EIC Recon is just not sufficient. And this is exactly the thing that will kind of be the main focus for the rest of the conversation is that this information that comes out of EIC Recon is not really what a physics analysis ends up being. This is kind of the bare minimum that comes out, and then everything after that is really trying to figure out how to make it something that can be used for physics. So the first concept that's really important here is really two things. It's acceptance and efficiency. Um, I'll talk a little bit more about the difficulty with efficiency near the end. So most of what we'll talk about here is mostly due to just simple acceptance because we're just looking at a single case with the protons. But ultimately, when we reconstruct something, our detector is going to be wrong by some amount on multiple fronts. It's going to miss the particle potentially, which means that it didn't detect it, and therefore the information it has is wrong by definition. And also the detectors have a intrinsic resolution that is not perfect. You'll have some smearing in every quantity that you reconstruct. And ultimately, these two things are not necessarily fully related. One is related to how much the detector actually covers in terms of phase space, while the other is related to the technology choice or its capability. And then efficiency is kind of a more complicated concept. In principle, at the very simple level, the efficiency is if a particle hits your detector, how often do you actually see it? Most particle detectors these days are incredibly high efficiency, but we want to combine information from multiple detectors, and that will inherently mean you have some efficiency loss that is not specific to the particle's acceptance. And we'll talk about that a little bit later. But ultimately, the acceptance part of this is really important because this is purely what we see here. This loss between the green, red, and black is purely from acceptance. And so we have to have an understanding of what the acceptance of the detector is so we can apply an appropriate correction. And so ultimately, if your production of particles is isotropic, let's just assume that it is, even though it's not necessarily always the case, then your acceptance correction is really just a ratio of your geometric coverage over the 4 pi coverage that you should expect for that isotropic production. And then efficiency is really just as simple as how many particles am I seeing within my acceptance, and you can test this from the simulations, for example. There are a little bit of a couple of cases where you do have some difficulty. So one is, what if your production isn't necessarily isotropic? So if you have a polarized set of beams and you have an asymmetry, that means that your acceptance correction is not as straightforward. And then, of course, if you have multiple detectors that are used together, let's say you're combining tracks and calorimeter information, that will lead to some acceptance loss because you're going to have some lack of ability to project those tracks to the appropriate calorimeter cluster. And if they don't match, then you don't keep it. And that means that you have a hit to your efficiency that comes from not the detector failing, but the failure of combining the information together. And that also needs to be understood if you're doing an analysis that requires that sort of thing. And so if we're looking at the acceptances, so now we're looking just at the t-distribution and we're just looking at the acceptances, so there's no smearing here. And then of course, like I said, you have to also have to think about matching information together if your detector requires it. And so what we can do in this case is just simply sum the information together in this magenta curve now. And the reason we can do that here is because the protons can't be in both detectors simultaneously. It's physically impossible. And so the particles that go through one detector and the particles that go through another, summing those together is the total acceptance that we have for protons in that region. And so in this case, it's very simplistic. And from this, you're able to construct a correction ratio that is purely driven by the acceptance and the very simplistic efficiency of just the detector being able to see the particles. And what you get is something that looks like this. It's literally just the ratio of the MC over the accepted. And you can see that the efficiency correction or the acceptance correction in this kind of mid region is huge because of course we have a massive gap there to be able to do the correction. I will say though, this is kind of an overly simplistic idea. What have I ignored here, right? I'm looking at a 1D distribution and its acceptance and trying to apply a correction. There's more that can come into why the acceptance is what it is in 1D. So in real life, a good example of this is if your detector has a chunk that's missing, right? So in 2010 in STAR, our time projection chamber, which is this big cylinder, we had a whole sector that was gone for the entire run, which meant that you had a phi dependence now on your acceptance. So if you were to look at the PT distribution, you wouldn't see that necessarily. You would only see the PT distribution. And so that's another thing that's really important to understand in these acceptances is what drives the acceptance loss. Maybe it's not such a simple 1D acceptance correction you have to consider. I'm only showing a 1D acceptance correction here for simplicity to make our lives easier in this discussion, but these are the kinds of questions you need to be asking yourself. Another thing that's really important within this kind of discussion of acceptance is whether or not you have an observable that is very sensitive to this sort of thing. And so, for example, if you have a spin asymmetry, the whole point with spin asymmetries is that you expect, hopefully, if the asymmetry is non-zero, you expect that you're going to have an excess of particle production in one section of the detector versus another. That's the entire point of what an asymmetry is measuring. But if one of your sections of your detector is not functioning during a period of time, you cannot measure that asymmetry. And so in some cases, a lack of acceptance can completely remove your capability to measure something. And that's also important for us to know. So if there's a thing you're measuring in CETUS, for example, and you want to measure an asymmetry, and there's an acceptance gap in exactly the wrong region, that's something we would need to know because that would inform maybe how we think about building the second detector, for example. If we have one region of phase space that's off limits because we have cabling for a detector that's in the way, or a flange from a beam pipe or something like that. So these kinds of things are really important, and you really cannot just look at the 1D information. I'm doing that because simplicity for this discussion. The other thing here too is backgrounds. All of this stuff will complicate your ability to come up with this nice, pretty easy acceptance correction. So, if you have copious particles being produced from backgrounds that can trick you into thinking that you found the particle of interest, but it's really from a background process, then your efficiency correction also ends up being wrong as well. It's really important that we think about these things in simulation now, because simulations will still be oftentimes how we actually come up with corrections for these things and apply an appropriate systematic. So right now, in many of the experiments that are existing, what is done is we have a simulation of the full detector, and that simulation can generate an output file that has the same format as the real data. And the idea is that you simulate the thing you want to measure. So let's say you're looking at JSI, you can take JSIs, embed them via simulations into a real event. So you take a real event, you simulate the JSI and the fake one, and you combine them together. And then you can see how good of a job you're able to do actually extracting the signal that you know is there because you put it in there under realistic detector conditions. And that's a way that you can estimate, the kinds of acceptance and efficiency losses you may or may not have. And so that's why these simulations can be so important, not just now, but also as we start operating Epic in the future. And so that's why it's important for us to really be thinking about all of these things as we do our analyses today, because we'll be doing the same kinds of things when we actually start taking real data with the EIC. These corrections will still be important, and we'll still use a simulation framework to do the corrections. And so anything we can do now to improve our understanding will help, because ultimately, the better we understand it now, the easier it will be to do analyses in the future. So after applying that correction, so just to remind you what we started with, this was the acceptance that we had in magenta, and then the black is the Monte Carlo. So the ratio of that gives us this acceptance correction distribution, and then multiplying this by the fully reconstructed distribution, which is what you have in magenta here. So that acceptance correction is multiplied by this magenta curve, and that gives you what's in green here. And you can see right away in some region, you have a really, really, really nice job of being able to correct back to what you should expect for the slope and normalization. But there's a region here where you still have quite a bit of bin migration. Part of that is from uncertainty just due to the fact that you have so few counts in this region of low acceptance. Part of it is due to the detector smearing. Those things both play a role. And ultimately, this is why it's also important that you have a good handle on your uncertainties that you have here, because when you try to perform this fit, that will also play a role. And so when you calculate your uncertainties from the acceptance correction, you need to make sure that you do it accurately. And ultimately, what you have left over after you've done the correction, you can still see some obvious migration in the binning. And that makes sense because we haven't corrected for that part. All we've corrected for is the acceptance. The beam effects that are present in the samples, the detector resolutions, those things are all still there. And so ultimately, if we want to try and handle those components, that's where an unfolding can help. An unfolding basically is able to characterize the full response that you have from measuring something using a simulation. And then you can build an unfolding matrix that can be used to correct also for the bin migration. It will apply systematic uncertainty, of course, because you're going to have some, good and bad way to do this. But those smearing and bin migration effects, that will be the leftover parts that could potentially affect your slope, for example, if you try to fit this distribution. And then the other thing here that I've not shown, and you see that I very conveniently left anything off of the y-axis here because this is still just a distribution of counts. I haven't done anything to actually make this into a cross-section. And so to make it a cross-section, you still need to apply the Lumi factor for this. So in this case, it's a 10 inverse femtobar in luminosity, and so we need to apply that factor to this, and then also divide by the bin width to make it into a d sigma dt that is actually representative of a proper cross-section. The other thing that's missing here is systematics. We're still quite early in EPIC's development to have a full handle on systematics, but one thing that's going to be really important is because the EIC will be so high luminosity, even in the early days, it'll still be well over 100 times more luminosity than what Hera was able to deliver. Um, the ultimate thing here is that many analyses will be limited by systematics, not by statistics. Now, JSI production is one that will likely be limited by both because it's a fairly rare event. But an average measurement in EIC will be limited by the systematics. And so starting to think about what systematics we have to consider, how big of an effect they might have. This is going to be very important. And anyone who's done an analysis with an operating experiment knows that this part is not trivial. And this ends up sometimes taking as long or a similar time that the actual analysis takes because you essentially have to rerun the analysis multiple times with different kinds of cuts and variations to understand how sensitive your observable is to those cuts and variations. There's also background conditions and running with different luminosities. All of these things can affect it. What's different here, so if you kind of look carefully as I go back and forth, you see that the green is moving around a little bit. What I've done here is I've purposefully made the Roman Pots reconstruction slightly worse. I basically just hand smeared the values by a little more than what comes out. And the point there is that you can see kind of directly how this impacts the remaining bin migration. And this is just once again to kind of point out that the acceptance correction doesn't account for this. And so this acceptance correction will basically make it really clear how good or bad your detector is doing and how much the beam effects play a role. Because the beam effects do play a role in certain observables more so than others. And after you've done all of those things, then you are able to start looking at doing a fit and doing something like a Fourier transform in this case for the physics that we're looking at here. And so you can see here now it's an actual cross section, so it's been properly scaled by the bin width and the luminosity. This is for a different sample. I didn't have the thing done for the one I'm showing today, but the process is exactly the same. But this can only be done once you've corrected all of the output and have some understanding of the full set of error bars, including systematics, and then you can actually go through and do fitting and see how good of a job your fit is doing and how good of a job you can do at extracting some PDF information, for example, in this case. So I think the main take home from this is a very simplistic example because ultimately I'm looking at a single particle final state. I'm not including many aspects of this. But even in this simplistic example, there's a lot that you have to do to go from the output of EIC Recon to something that is tangibly useful for the pre-TDR or for a publication. The physics working groups are now working on how to standardize these things. There's already been a lot of discussion on this, but these are the kinds of things that are going to be required for your analysis to kind of pass a bar to be able to be presentable at a conference or go into one of the EPIC publications. There are a few things I've excluded though. So before I start talking about those things, do we have any questions about anything I presented up to this point? Okay, it's all perfectly clear. That's great. Or I'm talking too fast, one of the two. So there are quite a few things that are excluded from this because ultimately some of these things are not even ready to really start including. So I talked a lot about beam effects and detector effects. What I mean by beam effects are that when you actually accelerate the particle beams in the accelerator before they collide, you have some uncertainty in the basic information. So in your particle physics textbook, you expect it's a perfectly longitudinal beam, and you have two of them, and they collide, and that's it. But in real life, you have some uncertainty in the longitudinal momentum. The accelerator's not perfect, and so you'll have some width to that distribution. There's also a transverse momentum that is inherent to the beam because the beams are not, a perfectly continuous stream of particles. They're puffs, they're clouds of particles that have a shape. And we squeeze them with quadrupole magnets to try and keep them nice and small so when they collide, we have high Lumi. But the actual act of doing that will cause them to basically push back against that squeezing, and you'll get some inherent transverse momentum as a result. And so when you actually look at what that results in something, why is my thumb coming up on the thing? When you look at what that results in terms of a distribution, if you have some intrinsic transverse momentum and you go to measure something like a t-distribution, that will clearly have an impact there because a t-distribution is purely the transverse part of the momentum for the most part. And so that'll have a huge impact there, for example. That's already included in all of our simulations. The afterburner includes all of those effects, but separating those effects from the detector effects is not necessarily trivial. And that's important for us to understand because if we have an intrinsic resolution from the tracking detector in EPIC and we have an intrinsic smearing from the beam, there's an interplay between those two things. But when we set our requirements, when we set our understanding for the performance, it was based on not having those components in. So now when we do measurements in our simulations, those things are all included. And so the resolution that we get now is kind of a convolution of all of the possible effects that we know anything about and are included in the simulation. So for these things to be disentangled, whether or not it's relevant to do that, it really depends on your working group and it depends on the thing you're measuring. And so these are the kinds of questions you should be asking to your working group and to your conveners when you're putting something together for an analysis. There's also requirements on finding your events. So for the exclusive physics working group, this is easy. We're looking for very specific final states. But another way to think about this, if you're from previous experiments, is trigger requirements. So you have usually, now we're moving away from this with streaming readout, but most experiments are still using triggers. You basically have some detectors whose only job is to tell the rest of the detector if something is interesting. And those triggers are basically set to look for certain kinds of events, whether it be a certain kind of topology, whether it be a certain number of tracks, whatever. So for example, if you want a trigger that specifically reads out really high centrality heavy ion collisions, ones where the collision is very head-on between two lead ions or two gold ions, you'll produce a lot of tracks. And so we used to have a trigger in STAR that was called like a high centrality trigger or a central trigger. And all it did was say, do I have a certain number of tracks in a time window? And if I did, I kept that event. Now, these kinds of requirements, everything that you normally would need to identify your event, even if you don't have a trigger, you're going to have some requirement. Those things will affect your ultimate efficiency for finding those events. And so to amend the process that we talked about earlier, the full analysis would look something like this. You first would find any event with a four-particle final state, right? So you have a scattered electron, a scattered proton, and then the J-psi to lepton pair final state. So that's four particles. So I would start by finding the proton because that's easy. It's either going to be there or not in the far-forward detectors. It's the only thing that could be there. And then you have to check after you found it that the other three particles are indeed leptons, and then you first should be finding the scattered electron because that's the most important thing for anything we do in DIS. And then you'd calculate the kinematic quantities from that, x and q squared, because you might want to bin your analysis on that. And after you've done those things, you've now said, okay, I do have a proton, I do have a scattered electron, I'm pretty happy with those. Now you see, okay, do I have two leptons remaining? Are they unlike sign charge? They have to be in order to be, possibly a J-psi. And then you can perform a reconstruction for the invariant mass. At that point now, you've found some group of events where you found all these things to be true. Everything between step 1 and 5 would lead to a loss of some of your events. So this selection has an associated efficiency. You'll lose events because there will be some events where you miss one particle and then the whole event is useless for this type of measurement. After that, you can then look at your J-psi distribution and put a cut on the J-psi invariant mass window and see if you have something that looks like a good J-psi. That will again mean that you lose some events because that cut is kind of arbitrary, right? You have to make a selection based on your understanding of the normal width of the J-psi distribution, how good your detector is at finding them, whatever it might be, and that will lead to some loss in efficiency. And you can vary that, and that can be part of your systematics. And only then, after you've done all these 6 steps, would you actually reconstruct the t-distribution. Because now you know you have some events that are worth reconstructing. And ultimately, everything would lead to, by step 7, a worse efficiency than what I showed above, in addition to your acceptance, right? And then you can start analyzing and applying your corrections and unfolding. This right here is kind of the next step in terms of understanding the full performance of Epic, because now you're looking at your ability to see a 4-particle final state for this measurement. You're looking at the smearing that's inherent in all of those reconstructions, because now the JSI mass is going to have some smearing to it, and that'll potentially pollute your ability to be able to identify JSI cleanly. Your scattered electron could have some smearing, and if you have a slight, incorrect calculation of Q-score, you could put something in the wrong Q-square bin, so on and so forth. And so when you're doing these analyses, this is really what the set of steps looks like for something simple, and this is a simple final state. Um, but in real life, this final state would be sitting in a fairly large background, so it might be kind of hard to find. And that's the last thing here that I haven't really talked a lot about, and that's the backgrounds. So there's machine backgrounds, which we're working on now, kind of integrating with the real events we already have kind of set up in Epic. So this is things like beam gas. So, you try to pump all of the gas out of the beam pipe, but you don't get all of it. And the beam pipes will get hot as things like synchrotron radiation hit them. And at some point, you will have some rate of beam particles hitting gas inside that beam pipe. And that will produce a fairly high rate of collision events that are not from the thing you care about. And those things will go into the detector, and they'll be distracting you from what you're trying to find. That's something we'll have to start thinking about as we actually start getting those merged events, but that's going to be important. But then there's also things like other processes which can contaminate your ability to find what you want. So for example, with DVCS, pi zero production, exclusive pi zero production is a huge background to DVCS, because you can have cases where you have a pi zero that's produced and the 2 photons merge into one calorimeter cluster, and you mistake it for a DVCS event. This sort of thing is a little different. You have to, be able to actually run exclusive pi zero production and DVCS and get an idea of what the contamination is, for example. So some of these backgrounds, like from the machine, are ones which we, as a collaboration, will figure out how to actually mix in to all of our events. Other ones are ones which you, as an analyst, have to figure out how to deal with. And so for the JSI case, we would want to look at other final states where you could potentially mistake something that is not a JSI for a JSI, like rho production. Now, rho production could potentially produce 2 pions, so you'd have to get both of them wrong as electrons, but it's a possibility and something you should have to consider, right? So ultimately, what we really need in all of these things are a set of standards. I talked about this in Frascati. This is basically just me repeating this information again. The working groups are working on these sets of standards now, but it also includes not only standards for your analysis, but also things we might be missing in EIC Recon. And so as you do your analysis, if you see a thing that I need is missing, that you want to have control over to see how it affects your analysis. A good example would be you want to know how many hit points are in your track to see how good of a fit your momentum extraction would be for that track. Now that information should be available, but that's an example of something that if it wasn't there, you couldn't, vary it and see how it affects your analysis. Um, and so as you do your analysis, if you see something missing, don't assume that it's, something that can never be put in. This is the kind of thing you bring to your working group and say, hey, for my analysis, I could use this information. And then they can give that to the software group to try and add. There's also questions about how you actually reasonably vary parameters. It's not the case that everything has a big effect on your measurement. So, for example, with talking about this, uh, the JSI signal may be very clean. And so maybe having, a broad range of cuts on your JSI invariant mass isn't necessarily so useful. But just an example. You should still look at it, but you might find that you're fairly insensitive to it. That doesn't mean something is necessarily broken. It could just mean that there are certain things that are not going to be a sensitivity for your measurement. But ultimately, varying parameters for reconstruction, for any of your final state particles or observables, that's part of what goes into evaluating your systematics. And so one of the things that the working groups are starting to work on now is compiling kind of a general list of things that should be considered for people to use. But if you've done analysis before in an experiment, think along the same lines. So if you're a postdoc and you've done an analysis fully all the way to the end before, you'll have done this before, and it's not really going to be drastically different, even if there are some specifics that could be a little bit different. Um, because we have a mature simulation framework, a lot of these things we can start doing. We're in a better position than many collaborations are at the beginning of their life because we have a framework that has a lot of things already existing and we can continue to improve it. I should also say here that I said this earlier that the working groups can really help us detector people, improve our reconstruction, but also evaluate if something is really wrong in the placement of a detector or the particular technology choice. It's unlikely we're going to find something that's really groundbreaking at this point. We've tested a lot of things, but we're moving into a phase now in the next 6 to 8 months where we're going to be kind of finalizing things to a point where they can't really be changed. That means we're going to be baselining what we're going to build. And that's kind of really the main priority for this year for the EIC is to make sure that we achieve that baseline. And so the next few months are going to be crucial for us to weed out any last minute things that are deal breakers. And so as you're doing your analyses, it's very, very, very important that you are thorough and being able to walk through the various different quality assurance plots I mentioned earlier. So your conveners can see, hey, there's something that's really wrong, and we can get feedback on it to make sure it's, uh, you know, either something that's to do with the simulation framework, or maybe it is something with the detector assumption itself. And so the convener's jobs is to really help kind of filter all that, but it's analyzers' jobs to try and make sure the conveners have the information they need. And this is really an ongoing discussion. So things I presented today are much of it is my opinion on how to approach things. Um, but the working groups are working on right now trying to put in a set of um, standards and guidelines that will eventually be endorsed by the analysis coordination team, which are the top level management. And so if you have experience with doing these kinds of things and you have feedback for something that could be missing, present that to your working group so we can also take it into account. It's very likely we're overlooking something, and that's why it's good to have people from different experiments also involved so we can make sure that we're not missing anything important. So that's the end of the official stuff that I had prepared. I'm happy to take questions. No questions. It's all fully clear or unclear, such that you don't want to ask anything.
Hey Alex, this is Mohammed from ODU. Yeah, thanks for putting this together. This is really very nice. Just one comment on the bi-zero contamination. It's true that some bi-zeros where the two photons get reconstructed in the same cluster is one of the main contamination to the DVCS channel in general. But mostly the contamination is for the case when only one photon of the bi-zero got reconstructed. That is the biggest contribution to the contamination from bi-zero for DVCS, from my
That
experience.
that might be true for fixed target. It's definitely not true in Epic.
Okay.
So yeah, that's the benefit of having a 4 pi detector is that you very rarely miss one of those two particles because we have calorimetry that basically is, for all intents and purposes, hermetic. It covers pretty perfectly between -3.5 and 3.5 with a very small number of cracks.
Nice.
The primary issue is at the top beam energy. The pi zero production opening angles are small.
Mhm.
Um, but the pi zero cross section in that area is also in a region of phase space where you can actually throw it away pretty easily just based on kinematics. What we found in our DVCS study that we just put on the archive recently is that at the lowest beam energy, you can have a non-zero amount of contamination that has to be accounted for that is almost entirely coming from mistaking a merged set of gammas. We find very, very, very few where you miss a gamma.
Nice. Well, nice. This is really nice.
Yeah,
I didn't.
because I would have thought it was a much bigger contribution as well, and it was actually quite strikingly small, even with accounting for some of the services and stuff that are in Epic that could potentially block one of the photons. They're high enough energy to where they're able to mostly get through that stuff.
Beautifully confirmed. One more thing. I'm sorry, I have missed the first part. I was in another meeting. So I have interest in doing the feasibility study for the production out of the helium target. But for the case of the helium detection in the final state, can you briefly update us how well the design concepts will be helping us in detecting such final state particles heavier than the proton?
Well, so it depends if you're talking about a coherent
Yes,
intact nucleus. So if you're looking at a
coherent.
coherent
Coherent
intact
and
nucleus,
incoherent, but mostly the coherent.
so for the coherent part, it's pretty challenging, even for the light nuclei. We looked at this for helium-4 years ago,
Mm.
using TOPEG, and the angular distribution that TOPEG produced for coherent helium-4 had a very low acceptance in the Roman pots. And this is primarily due to the fact that it's a small angle already because it's a slightly heavier particle, but also the beam optics that you have don't allow you to get as close to the beam. Now, to be fair, we don't have what I would call the most optimal beam optics yet for every single possible beam species that we could hope for, so it might improve. But overall, coherent detection of the intact nucleus in the Roman pots is fairly challenging. For deuterons, helium-3 and helium-4, it's definitely possible, but
Mhm.
with every increase in A, it drastically becomes more difficult. So,
So do we have any group that you are aware of who are working on this? So it's better to align our efforts here with ongoing efforts rather than everyone to be running in parallel space where we don't know about each other.
to my knowledge, no
Because
one that I know is
because
working on coherent helium-3,
yeah.
but it would fall under the exclusive physics working group. So if you're going to be doing simulations with that with Epic, that's where it would be presented and vetted.
Yeah, because the only effort that we have done for the detection of like the helium-4 was for the yellow reports when we have done just a feasibility study. We have used Topic event generator, but it was mostly to see like what will the detection threshold on the helium-4 will affect the extracted quark profiles for different slices in X. But in reality, we did not simulate anything. We have just said that if this momentum threshold, like for instance, I do remember I had the three sets, like on the transverse momentum of the helium-4 to be greater than 100 MeV, 200 and 300 MeV per C. And then we have checked what this will reflect on the extracted profiles. But yeah, we didn't do any simulation for this before. And
Well, the,
yeah.
the basic tools to do those simulations do exist, and so it should be fairly straightforward to look at something basic like the acceptance of what you actually
Mhm,
get in the detector.
mhm. I'll
And
reach
yeah,
you. I'll reach you
okay.
for additional information. But yeah, I just wanted to highlight these couple of points because yeah, it's more effective if we align the efforts rather than everyone will be working on his own work. Okay.